This is Dr. Holt. In this rotational kinematic problem, I have a dentist drill that starts from rest. After 3.2 seconds of constant angular acceleration, it turns at a rate of 26,000 revolutions per minute. I want to find the drill's angular acceleration. I want to find the angle through which the drill rotates during this period. I want to find the tangential velocity at 3.2 seconds if the diameter of the drill is 1.6 millimeters. And I want to find the tangential acceleration at 3.2 seconds, and I want to find the centripetal acceleration at 3.2 seconds. The first thing we want to do here is we want to change this angular velocity from 26,000 revolutions per minute to radians per second. And to do that, I will come down here. I will take the 26,000 and again, that's going to be revolutions per minute. We'll do a unit conversion. I got revolutions here. I'll put 1 revolution here in my denominator. I'll put 2 pi radians here, because 2 pi radians is the same thing as 1 revolution. We got minutes in our denominator here. We'll put 1 minute here. And we'll put 60 seconds here. We will do the math. And when we do that, we will get 2,722.7136. And that'll be radians per second. Okay, that value there, again, will be my angular velocity. All right, now we want to do is we'll go back to the problem. We want to find the drill's angular acceleration. We will go back to our kinematic equation for rotation that says this: the angular velocity at a time interval is equal to the angular velocity initial plus the angular acceleration times time. We know at 3.2 seconds we're going to have 2,722.7136 radians per second. Set that equal to our initial. Now we know that our initial here was 0 because we're starting from rest, and I think that's stated in the problem right here, starts from rest. So we know this goes to 0. So we'll set that equal to 0 plus my angular acceleration times my time of 3.2 seconds. We'll divide this side by 3.2 seconds. And when we do that, we will find our angular acceleration will equal to 850.848. And those units will be in radians per second squared. Okay, again, that is our angular acceleration. And that angular acceleration here is going to be constant. And we reach the velocity, angular velocity again at 26,000 revolutions per minute, or 2,722.7136 radians per second. All right, so we have the first question solved. Now it says find the angle through which the drill rotates during this period. We will go back again to our rotational kinematic equation. I'll extend this down just a little bit. We'll go back to the one that says our angular position is going to equal to our angular initial position plus our angular velocity initial times t plus 1/2 times our angular acceleration times t squared. Again, we know we're starting from rest. We'll let this be 0. Our angular velocity, we know that is going to equal to 0. So all we're going to have in this equation is our position. Angular position is going to equal to 1/2 times our angular acceleration times time squared. So our angular position will equal to 1/2 times our angular acceleration of 850.848 radians per second squared times our time, and our time is going to be 3.2 seconds. We will square that, and we will get a value here of equal to 4,356.34 radians. Again, we can convert that to our degrees if we choose to. And to do that, we'll say 4,356.34 radians. We got radians here in the numerator. We know there's 2 pi radians in 1 revolution. If we do that multiplication, you notice that our radians here will cancel out here. That'll give us our units and revolutions. And we do that, we will get 693.33 revolutions. Alright, so that's those 2 answers. That will be our answer in radians, and that'll be our answer in revolutions. Alright, that's the second one. Now we want to find the tangential velocity at 3.2 seconds. To do that, we know that our tangential velocity is going to equal to our angular velocity at that point times our radius. So our velocity tangential is going to equal to our angular angular velocity, and we said that unit was 2,722 right here. Put that in as 2,722.7136. That's radians per second. We'll multiply that by 1.8 meters. Now we need to divide that, that's millimeters. We need to divide by 2 because remember that's our diameter. And now we don't want to leave that in millimeters. We can. That'll just, if we do that, it's just going to give us our tangential velocity in millimeters per second. But we'll go ahead and convert that, and that's going to be, we'll multiply that by 10 to the 3 meters over 1 millimeter. And again, our millimeters here will cancel out. And I'll run that calculation. And our tangential velocity will be somewhere around 2.45 meters per second. That'll be our tangential velocity. Alright, so now we're down to here. We got that question. Now we want to find the tangential acceleration at 3.2 seconds. To find the tangential acceleration, we know that acceleration tangential will equal to our angular acceleration times our radius. So we will go back, and to work that problem, we will get our angular acceleration, and again we said our angular acceleration was what, 850.848. And that's radians per second squared. And we will multiply that by 1.8 millimeters. We'll again divide that by 2, be real careful with that, times 10 to the minus 3 meters over 1 millimeter. Again, our millimeters will cancel out here and here. And let's see what kind of value that's going to give us. Sorry. That one I left out of the calculator. That's going to give us a value of 0.765. Again, the units are going to be meters per second squared. And that would be our tangential acceleration. Now again, if there's any confusion about what I mean when I mean tangential, if I draw just a circle looking at, oops, let me draw a better circle than that. I draw a circle looking at that. The tangential velocity and acceleration means it's going to be perpendicular, or sorry, not perpendicular to the radius. I can draw that a little straighter, sorry about that. It's coming up like this. It's going to be, and if I drew the radius, it'd be from here in. Again, it's going to be exactly right angle, be tangential there. The tangential acceleration and velocity would be a vector quantity, and it would be tangent to the diameter of the drill bit. All right, so we got, see what we got here. We got this one done too. And now the last thing is find the centripetal acceleration at 3.2. We know from previous sections that we can find centripetal acceleration, and centripetal acceleration is going to equal to the velocity tangential squared divided by the radius. So we know the tangential velocity we said was, what was that, 2.45? So we'd take 2.45 meters per second. We will square that. We divide that by the radius, and again, the radius we want to convert this, and that's going to be 1.8 divided by 2. So this time I'm going to make it into 0.90 times 10 to the minus 3 meters there. Again, that one I have not run in the calculator. I'll run that real quick. 2.45. We will square that. Divide it by, in parentheses, 0.9 times 10 to the negative 3. And that's going to give me a pretty large value, actually, of 6,669.44 meters per second squared. Interesting problem here, because if you tried to find the net acceleration in this problem, let me get rid of this. You would have a vector going in to the center that's going to be this one will be much larger than this, and this one will be extremely small. And if you try to use Pythagorean theorem to find out what your net acceleration would be, it would still be pretty close to this number because of this value being so small. Anyway, hope this video was useful. It's again just an example of how to use rotational kinematics in a problem related to a drill bit. As always, I wish you the best of luck.